too early, but yeah, we're talking about parallelization. Anyone knows about parallelization? Oh, only one. Oh, God. OK, so there's going to be a quiz for you at the end of the talk about parallelization. If you win the quiz, we will. I don't know, who's the conference host? Can we give them something if they win the quiz? A voucher? A sticker? No, no, maybe food. Or like, I don't know, beer or something. Anyway, go ahead.
Okay. Hello, everyone. So it's my great pleasure to explore some of our latest ideas on top of the parallelization EVM. So, oops, let's have to move. Upon here. OK, great. A quick intro of myself. Has been working in this area for about 6 years, previously working primarily in some big companies in parallelization, high-performance systems, got a PhD. And so that's why I'm particularly interested in, for example, Ethereum data availability, layer 2s, all those scaling solutions, and got a couple of supports from Ethereum Foundation. So, what's going on? Oh, I guess I used the wrong direction. That's why. So, oh, I guess this is the wrong link. OK. OK, great. Yeah, so why we want to particularly interested in parallel EVM? So it basically would like to answer some ultimate question. What is the ultimate performance of EVM if you don't have any overheads of the fixed XML consensus? Which happens, like, for example, right now for layer 2s, all those sequencers can just produce the block in almost instantly. And so there will be a lot of questions about, in these scenarios, how would EVM can achieve what maximum PPS in this setup? And also, another question is that, are we able to build an EVM that is even faster than, like, for example, Solana? And there's a lot of this question flying around. And so people say, hey, why not use some Web2 experience to accelerate the execution? Especially right now, we are heavily relying on, for example, parallelization in order to speed up those transactions. So in the parallel EVM, there's generally two categories. One slice in called parallel execution, or sometimes called optimistic execution, which basically to execute a sequence transactions, future transactions. For example, we have A, B, C. Then the normal way is I execute one by one. That's called sequential execution. That's what have A, B, C, but it's slow. Then the parallel execution say, hey, why not we are able to running A at the same time, we also execute B and C using the state that the A actually is executing. And once after executing A and B, then you just double check if there's a conflict of the read and write set. And if not, then you can just easily merge the execution result of B with the A's result so that we can get the corresponding results, and that is able to better to utilize the current parallelization concurrency feature of the node. And another direction is called parallel I/O, which aims to reduce the latency and boost the performance using some technologies. So why we want to study or accelerate the I/O of the Ethereum? So here is a really nice chart from MEV, that is Flashbots, that shows what are the major normalized runtime that would be used in the basically in the EVM execution. And this is using the mainnet data, so you can see the corresponding block numbers. And so they list a couple of the major OP codes. And the last one here is called OPS low, which is basically reading 32 bytes of the data from Ethereum by given a key. For example, I read a user's balance account, or read the ownership of the, for example, NFT images. And all this access code actually accounts for approximately about 70% of the EVM execution, which means that even though we are may be able to accelerate the, for example, other executions, like for example, by using a better way to interpret the OP codes or other ways, we still have a large amount of overhead in this SLO operation. Why? The reason is that the EVM I/O patterns is very unfriendly for the I/Os. First of all, a lot of these I/O are random access patterns, which is hard to predict. For example, when I read a balance of Uniswap balance of some, for example, the pool balance, then the Solidity actually will generate a random position using Keka and the corresponding key to randomly locate a position of the data in the database. And such kind of a random access is really, really unfriendly for the underlying database storage. And second, the Patricia-Merkle tree that Ethereum now uses further worsen the case of random access because the random tree, its structure is also highly randomized. And so in order to solve this problem, there are a couple of the pioneer ideas that aims to say, hey, whether we are able to figure out a way to reduce the latency that when we read the random positions. One thing is to, hey, rather than just have these random positions or locations during the EVM execution, why not we are able to, using token kind of incentive, to let the sender to specify called access list, which can tell the EVM that, hey, there are some data that I'm going to access ahead of the execution. And now the EVM can parallel loading this data from this access list so that when reading this data in the later, it's already in the cache. So reading the data will be generally in the cache will be generally takes zero latency. And hence, we are able to significantly reduce this I/O speed. And so in our test, it can enhance the EVM execution. Suppose we have full access list, we can increase the performance about twice with all those very simple strategy. And this is a really nice idea, and this is also proposed by Vitalik about, I think, 2 or 3 years ago. But unfortunately, there's a paper that is written by ETH Zurich. It's a university, it's not an Ethereum sub-organization. So there's a really good paper saying that they do a lot of study on the mainnet optional access list. And they found, even though there's a great feature to accelerate basically the transaction execution, it's highly underutilized on the mainnet with only about 1.45% of the transaction utilize this feature. And there are a lot of reasons. One reason is that because the current incentive of incorporating this access list is very, very minimum because it increases the core data price. Because have more data, then the Ethereum needs to broadcast all these access patterns or access lists to network, and this has an extra cost. And so a lot of users found, if the corresponding cost of broadcasting this access list is greater than the cost that is a gas savings that this EIP brings, then definitely nobody would like to use this feature. And also there's a couple of things because it's a lot of client, execution client, return some wrong optional access list. And so then it may incur like even worse result. So if you are interested in this topic, especially like parallel execution, I think this is a really excellent paper to take a look and a couple of ideas which actually highly aligns with what I'm going to talk about. So in order to address these problems, especially underutilization of this access list feature, there are a couple of things that we are working on. One is to propose an EIP that is 7650, which is a really good name, easy to remember. The idea is to basically say, hey, rather than have the user to encode the access list in the transaction itself, why not we are allowed to program the contract to tell that, hey, I'm going to read these random locations of data but at the very beginning, and so that the contract, because the contract has the full knowledge what the future access pattern of the execution will be, then we are able to harvest the parallel loading and reduce latency, and further the sustained benefits, because every time it executes this contract, it will load using this parallel access list, programmable access list to load the corresponding data, so the benefit will be sustained. Another thing is inspired by Reason AI, and we also found that we are able to using some way to find a common access pattern so that we can be able to, even without program this data, but we are still able to learn what are the common random locations when execution, like smart contract call, will read, and then we are able to learn these things, and then load this in the future execution. So I will explain all this to you in details. So first of all, before we dive into details of how we are able to implement these parallel IOs, one thing I would like to highlight is about what are the underlying storage, how many parallel IOs the underlying storage can offer. So here I just give a commercial commodity 4 gigabytes NVMe SSD, which is about $300, I believe every node can offer. And so I run some parallel I/O program, which is the famous FIO. And so this will tell us, hey, how many IOs that I parallel issue to the underlying storage, and what is corresponding latency there for each random access, so that we can tell that how much parallelization we are able to achieve in terms of I/O using the commodity like disk. And we can clearly see that if even we just increase the number of random IOs to, like, for example, 12, more than 10, the number of the latency increase is just very, very minimum. And for some numbers, like 4, is almost basically the same, which means that if I can suppose I sequentially read this random data, or I run this data parallel in 4 IOs, they actually use the same latency when reading all this data, which shows the current capability of the NVMe disks that allows to high number of the random parallel I/O and random access. And so definitely you can also using the famous FIO tools to reproduce these numbers. But this tells us what is the ultimate optimization goal that we can achieve using a simple commodity PC. And definitely we can use even higher advanced, like using RAID 0 or using more advanced SSDs. But this is some number that we can easily get. So the programmable access list is allowed a smart contract to basically to specify which part of the data will be accessed ahead of the actual execution. So let's take a Uniswap swap as an example. The Uniswap swap, each time it will read five that is the storage slots, including the pair of the address pairs of the tokens, and reserve, which is basically a compact version of their balances. That is the token that has deposited into the contract. And price 0, price 1 accumulated last, that is using to calculate some I think statistics, some numbers, so that I think they are used to distribute some fee, all those things to the basically LP and also, the LP, I believe. So these 5 storage slots will be constantly read when calling a Uniswap swap. So suppose now we have a parallel I/O loading in a smart contract and also the corresponding OB code that is supported. So now we are able to start, when we start this call of method, we can say, hey, I'm going to read all this data, let's just prefetch all this data and ask EVM to say, hey, I want to read this data in the future. Please read this data ahead my execution. And this can also prefetch these two contracts to tell us, hey, I'm going to call these two contracts. For example, I want to check the balance of the token 0 and balance of token 1 of this Uniswap contract. Then please load this contract ahead before I call this. So we can list as much as we could. It can be combined with, for example, some parameter that is input, so that we can also load. So this is, you can see that this is as fixed locations. Every time it's fixed, but definitely we can combine with some input parameters so that we can know that what is the future access by the smart contract. And every time when they call the smart contract, we will automatically load all this data in parallel. So how we are able to, with this, now we basically reduce 5 random access into 1 random access. Suppose we are using some devices with this high performance, with this latency, because we can see that there's no latency increase with about 4 or 5 IOs, and which means that we are able to reduce these IOs. For example, suppose it's 70% of the execution, then we can reduce it maybe half or even less, because we are using the underlying parallel IO capabilities of this. And also, we assume the gas is the cost of the basic preloading is the same, parallel preloading is the same as a one sequential loading. Then we can enjoy a constantly gas reduction. For example, right now, 1 random access of the storage store, it takes about 2,100 gas. Then we are able to save to single 2,100. Suppose we assume this gas price is the same, but definitely there's rooms to tune. But suppose we have this safe assumption, then we can easily save thousands or tens of thousands gas per transaction. So this is the basic idea of parallel I/O. You can imagine it's kind of like traditional programming with kind of parallel like threading, all these ideas in the program by itself. And at the same time, we also observe that all these random locations, they are constant for each Uniswap call. And even without, for example, I tell that whether this location, they do not depend on any input parameters. So the idea is that would it be possible that we can have the EVM to learn those common read patterns associated with a method. In this case, is the swap method, which can be easily figured out by using the method ID according to the ABI encoding. So that we tell that for this method, this is common access pattern. For this method, maybe for example mint, this is another common access pattern. So that once we are able to learn this, and once this has become stable, then we can easily, using this idea to, for example, every time you call a method, find the access list, call another method, call a method next time, it will basically filter out this, find out the common list, and then for the future, they can use this this list to basically call all those smart contracts automatically without having any, for example, introduce new EIPs, just purely EVM optimization. And that's basically the idea, what we call intelligent I/O preloading, as we have observed a lot of patterns in a lot of smart contract, which has this constant common access patterns in the smart contract call. So here's my concluding remarks. In this talk, we explore 2 innovative strategies which aims to reduce the I/O latencies by enhance the access list, which proposed by Vitalik. The first idea is that we are able to allow the programmer to specify what is the future data locations that I would like to read, and please read this data ahead in parallel, so that we can greatly reduce the latency when we really read this data, because these data are already in cache. And the second idea is that given the method ID and also the contract, then we are able to learn, to identify what are the common access pattern of these contracts, and then just can automatically got the benefits of these parallel IOs. And so we hope that all these technologies, once we become mature in the future EVM, we are able to significantly accelerate the EVM execution, that definitely together with other features. For example, there is the just-in-time compiler that Mega that is developing, so that you can reduce the interpreter time to interpret the IO codes and then execute. So there are a lot of interesting ideas that's flying around, and that's all of my talk today. Thank you very much. I'm happy to.
Anyone has questions?
Yeah, questions, please.
Yeah, I want to ask, so parallelized EVMs has recently become more of a narrative in the context of other chains. So I was curious, given that you're kind of closely familiar with this, if you have seen some chain or implementation of this that you think could be long-term viable in terms of connecting, for example, Solana and Ethereum, because there has been Neon, Eclipse, and different kind of attempts at achieving this. So what do you deem the best effort at this right now?
So the question is about what is the best effort to make parallel EVM in production, right, or success. So first of all, I have one is according to my previous experience, trying to fix a lot of parallelization bugs. In general, takes a lot of time to make concurrency works correctly. So first of all, it's really hard to debug. And also, it's really hard to make sure that the code runs correctly, and also, for example, writing the test. So I think right now we are at a little bit early stage. One example I can tell you is that so Polygon has implemented their version of the parallel EVM in terms of go based on top of gas. And so we took a look at their code and study how it works. It's basically an idea of block STM, software transaction memory, using the optimistic execution. But two things we observed. We found a couple of bugs and fixed them. And second, like, oh, looks like there's some easy bugs. And I say, why not? It's happening in the production. And then later found, actually, it's still in the experimental stage. It haven't been used in their, for example, mainnet. So it helps to answer some questions. What is the ultimate performance gain using all these technologies? But still, in order to run in the production, then it will, I think it would take some time to, especially for some critical applications. I won't imagine Ethereum layer 1 will use it, because right now the bottleneck is consensus. It's not about the IOs. But as more and more layer 2s are coming, and definitely they are able to harvest benefits. And also there's the idea of called diversified client, right? Suppose I have a client that runs parallel EVM, and no other client can catch up. Then I have no idea when it enters something that's wrong. I cannot tell, because nobody can tell me, oh, sorry, the transfer balance is supposed to transfer 100 ETH, but because some parallel EVM is scheduling, it just transfer 10 ETH. But with the diversity client, so we have two implementations of client, but each of them can catch up with each other. And then it will be much easier also to figure out the problem. This is the same issue applies to ZK proving, because ZK proving is also using the diversified ZK provers, so that if something is wrong, then we can use a multiple prover to make votes rather than maybe people just using a multi-signature. So there are a couple of things to address this problem, but as an infrastructure, I think it's still in a very early stage. We need a lot of excellent engineers, excellent researchers to help to solve this problem.
Thank you.
All right, great.
From smart contract development point of view, do you foresee any downsides of using this prefetch? Like, are there any reasons why every new smart contract will not just like prefetch everything?
That's a great question. So I have developed a lot of smart contracts. One concern that as a smart contract developer is the gas. Because I really want to have other applications or other users run CoreOS. The gas can be saved in a really optimized way. That's why, for example, OpenSea, when they try to optimize their DAX on chain, they use the assembly code rather than Solidity. It's that because they have money to do this extreme optimization. And for us, I think if there's a proper way to reduce the gas using this explicit gas metering to save this gas, and especially those parallelization execution takes a lot of like execution runtime or wartime, and then so that like from the EVM perspective and also developers perspective, there's an interest alignment so that we want everybody to implement this feature so that smart contract developer can save gas at the same time EVM can process more transactions. So I think this is the ultimate goal, that win-win goal that both developer and the EVM protocol developers can be harvested from this approach. But how to determine the gas, for example, how many parallel loading that we are able to accept, whether it's 4 or 5 or maybe 10, that still leaves a lot of room to discuss. But I don't think that should be impossible, because we see that like 300 MEMD disk is already be able to support a large amount of parallel I/O. Yeah.
Another one from a validator perspective. Do you think it will increase the load on validator hardware? Will validators have to upgrade somehow, or like what is running now, it will suffice?
So the question is like what's the validator maybe had created concern that increased their nodes, right? Is that?
Yeah, I mean the load on their hardware, if they will need like more, I don't know, more storage or more memory or like yeah, basically, yeah.
So that is a really good question. For example, recently Arbitrum, they are having an issue that because they process too many transactions, so a lot of other nodes are not able to catch up with their latest transaction, even they're just running all those transactions 100%, because the sequencer or Arbitrum sequencer has much higher like hardware requirement devices compared to others. So that is really good questions. Actually, we run a lot of Ethereum nodes and to do a lot of experiments. I think I found there are some cloud providers that are offering some Ethereum-friendly devices with pretty much, I would say, really high performance, like 128 gigabyte memories with 16 cores, and about 7 terabytes RAID 0 SSD, can offer 7 gigabytes read and write. That takes about 70 euro per month. I think that should be acceptable, or something that we are able to design for this spec from our protocol designer perspective. That's my answer, yeah.
Okay, I was asking more about from perspective of home validators who run like who have hardware on the lower side, like of performance, so like rock pies and things like this, or ARMs. Yeah.
So you mean whether it increased the cost of home validators?
Yeah, exactly. Will it increase the cost of running home validator? Yeah, basically, yeah. Who don't have like big servers, or who don't pay like to cloud services?
Depends on what kind of home validators. Like for me, I kind of like a geek for computer. I assembly those things by myself. Yeah. I don't think it is hard to buy some cheap commodity devices. Like for example, I have set up like 4 SSD using Samsung 990, that which can easily offer 10 gigabytes read and write, with maybe less than 1,000. But definitely, actually, it's really great questions whether I suppose I would like to run it in the cell phone or some environment.
RockPi is very common.
Sorry?
RockPi, ARM-based.
Yeah, RockPi.
Box, yeah.
I do think right now is using the modularity layer solutions, so that for layer 2 they can run as fast as possible. But for layer 1, like for example, we can have the vertical tree, stainless list, like Milos is also working on that, so that we are able to allow, for example, maybe iWatch or some devices to vote at that time. The parallel EVM actually is not the major issue, like execution is not a major issue.
All right, thank you so much, Xi.
Thank you.
Did we learn about parallelization after that session? Okay, great, thanks. I learned something too. All right, next speaker is Tobias.